Hello students, welcome to Chem is Try. In this video, we want to focus on performing calculations involved in continuous double indicator titration. In our previous video, we realized we built we developed two tables for every double indicator titration. In the continuous table, we realized that we have a table for phenolphthalein and that one for methyl orange. We had an average titer for the phenolphthalein titration and another average titer for the methyl orange titration. But remember, we kept the initials at 0, although the titration was continuous. Today, we want to look at what really happens in double indicator titration, especially the continuous one. As chemistry students, we are all aware that when a dilute acid, like hydrochloric acid, reacts with a carbonate of a metal, for instance, sodium carbonate, it is going to undergo what we call a kind of neutralization reaction. The only thing is carbon dioxide will be evolved in addition to the salt and the water. So in this case, you are supposed to form sodium chloride, water, and carbon dioxide. But if you check the titration, when we're performing the titration, you realize when we added the phenolphthalein indicator and we're releasing the acid into the mixture, there was no effervescence that was observed, telling us that carbon dioxide wasn't produced in that reaction. However, when methyl orange was added, we saw effervescence of carbon dioxide gas. There are some things we need to know here. When phenolphthalein is used as an indicator, when sodium carbonate reacts with hydrochloric acid, only half of the sodium carbonate is converted to sodium bicarbonate. Remember, we should have neutralized it into sodium chloride, carbon dioxide, and water. But here, we are doing a shady business. We are not doing the right thing. When phenolphthalein is around, the work is shady. Instead of converting sodium carbonate to carbon dioxide, water, and sodium chloride, in the presence of phenolphthalein, it is rather converted to sodium bicarbonate. And this is the reaction. And it's not all the sodium carbonate. It's only half of it that is converted. So let's remember, the mixture in solution B is sodium carbonate, then sodium bicarbonate. And what we are saying is that in the phenolphthalein titration, we won't touch this one. But this one, we are going to touch half of it and convert the half of the sodium carbonate to sodium bicarbonate. And this is the chemical reaction. So sodium carbonate over there will react with the HCl in the presence of phenolphthalein indicator, and we are going to produce sodium bicarbonate and sodium chloride. Because it didn't do the complete job, it didn't neutralize all sodium bicarbonate. It neutralized only half of this one. And it didn't touch sodium bicarbonate at all. The end point came so quickly because we didn't do a thorough job. So let's assume that the volume of HCl that reacted with the half of sodium carbonate is Y in a phenolphthalein titration. Let's keep this Y somewhere. We will use it very soon. Now remember, let me talk about the Y. In our table, we had a Y as our average titer to be 5.05 centimeters cubed. That was our value for Y in the continuous titration. But let's assume we don't know. So, phenolphthalein has helped us to do an incomplete job. An incomplete job. Instead of neutralizing everything, it took just half of sodium carbonate. And even that half, it didn't neutralize it very well. Then, methyl orange came into the business. Remember, we didn't discard the solution. We just added 3 drops of methyl orange and continue the titration. So methyl orange came and said that, hey, phenolphthalein, why did you do this shady job? Okay, I'm here. I will make sure I'll perform the task thoroughly. So when methyl orange was used as an indicator added to the mixture, what happened? The remaining half of the sodium carbonate, methyl orange will make sure it is completely neutralized. Now, we have sodium bicarbonate there. Then, phenolphthalein converted half of the sodium carbonate to sodium bicarbonate. All the sodium bicarbonate there too, methyl orange will make sure they are also completely neutralized. That is the job methyl orange did. So one of the jobs methyl orange did was to take the sodium bicarbonate that was already present and the half that was created from sodium bicarbonate, added all of them, then converted them to sodium chloride, carbon dioxide, and water. They later came to deal with the sodium carbonate and converted the remaining ones to carbon dioxide, water, and sodium chloride as well. So, in effect, the overall reaction became sodium carbonate reacting with HCl to form sodium chloride, carbon dioxide, and water. So, when methyl orange came into the business, the remaining half of sodium carbonate converted. All the sodium bicarbonate present also converted to what? Sodium chloride, carbon dioxide, and water. Now, because methyl orange is doing the job thoroughly, it took time before we reached our end point because methyl orange had to take its time. Hey, have sodium carbonate remaining. Let me convert you. Hey, all the sodium bicarbonate, come around. Let me convert you as well. Because of that, the end point was somewhere around 21.05 centimeters cubed. Because methyl orange did a complete job. So let's say that when we added the methyl orange, the volume of HCl that was needed to convert the remaining half of sodium carbonate and all the sodium bicarbonate to sodium chloride, carbon dioxide, and water. Let's make that one X. Now, let's represent this information more pictorially so that everything becomes simpler for us. Or, yeah, let's make it simple for ourselves. Let's make it simple for ourselves. So, what we are saying is, Y is the volume of acid. Let's say this is our Y. Our Y is the volume of acid that was needed to do what? To neutralize half of sodium carbonate. That is what we have said. Then we are saying X is the volume of acid that was needed to convert the remaining half of sodium carbonate and all sodium bicarbonate to sodium chloride, carbon dioxide, and water. That is what we are saying. That is what we are saying. So why, as the volume of HCl used in the phenolphthalein titration, that HCl did something. It converted only what? Half of the sodium carbonate. It worked on only half of the sodium carbonate. Then we are saying that the volume of HCl that was used in the methyl orange titration did something. What did it do? It converted the remaining half of the sodium carbonate and all the sodium bicarbonate. Converted all of them to sodium chloride, carbon dioxide, and water. That is what we are saying today. So we have that one too presented nicely over here. X is equal to half sodium carbonate plus all sodium bicarbonate. Now, from this first one, we can say that If half of sodium carbonate is equal to Y, what will be complete sodium carbonate? Simple mathematics. Let's multiply here by 2 and here by 2. So all sodium carbonates become 2 times Y. 2 times Y. Let's keep this thing somewhere. All sodium carbonate is equal to 2 times the average titer in the phenolphthalein titration, which is represented by the letter Y. So if we need just Y centimeters cube of HCl to neutralize half of sodium carbonate, then to neutralize all sodium carbonate, we will need how many? 2 times Y. Very simple math. Then let's look at this one. X is the volume of acid that was used to neutralize the remaining half of sodium carbonate and all sodium bicarbonate. So if we want to know the volume of acid that will be used to neutralize all sodium bicarbonate, we just have to make all sodium bicarbonate the subject. So all sodium bicarbonate is equal to X minus half sodium carbonate. But remember, half sodium carbonate is known as Y. Initially, it is known as Y. Half sodium carbonate is what? Y. So we can say that all sodium bicarbonate need a volume of acid which is equal to X minus Y. Now remember, our X is the volume of acid in the methyl orange titration. In methyl orange titration. And we know our Y to be volume of HCl in phenolphthalein titration. So if you want to calculate the volume of HCl that will neutralize all sodium carbonates, is 2Y. 2 times the average titer in the phenolphthalein titration. If you want to calculate the volume of acid that can neutralize all sodium bicarbonate, is X minus Y. That is volume of acid in the methyl orange titration minus the volume of acid in the phenolphthalein titration. So if we are asked from the titration we performed, what is the volume of HCl? Volume of HCl required to react with all sodium carbonate. All sodium carbonate is 2 times Y. So the answer will be 2 times Y, which is our volume of acid in the phenolphthalein titration, which we found to be 5.05. And that will give us 10.10 centimeters cube. If we are asked, calculate the volume of HCl required to react with all sodium bicarbonate, it will be given as X minus Y. That is, X is the volume of acid in methyl orange titration, which we found to be 21.05. Minus the volume of acid in the phenolphthalein titration, which is 5.05. And that should give us 16.00 centimeters cube. But the question is, how do we use these values to calculate the concentration of sodium carbonate, concentration of sodium bicarbonate? To do that, there are two chemical equations, two balanced chemical equations that we need. And here are the chemical equations. So these are the two chemical equations you will need. In the first chemical equation, we have a relationship between sodium carbonate and hydrochloric acid. So that one will help us to find the concentration of sodium carbonate. In the second equation, we have a reaction between sodium bicarbonate and HCl. So that one will help us to find the concentration of sodium bicarbonate. So let's name the equations equation 1 and equation 2. So let's first pick equation 1. Equation 1. So equation 1 is a reaction between sodium carbonate plus HCl to form sodium chloride plus carbon dioxide plus water. So let's call sodium carbonate solution B, because solution B was made up of sodium carbonate and sodium bicarbonate, but we are referring to just the sodium carbonate as B and hydrochloric acid as A. Now, per the mole ratio, we have 1 mole of sodium carbonate reacting with 2 moles of hydrochloric acid. So the moles of B over moles of A is 1 over 2. The moles of B is 1, moles of A is 2. So the moles of B over the moles of A is 1 over 2. But we know that amount of substance is concentration times volume, which means that amount of B is concentration of B times the volume of B. Amount of A is given as concentration of A times volume of A. So we can replace N of B with CBVB and replace N of A with CAVA. So this part becomes concentration of B times volume of B divided by concentration of A times volume of A. And the ratio is 1 out of 2. We can just simply cross multiply. Then we get 2 times concentration of B, volume of B is equal to concentration of A, volume of A times 1. Now we need a concentration of B. In this case, our B is sodium carbonate. So concentration of B is concentration of A times volume of A divided by volume of B times 2. Over here, Ca is the concentration of HCl. Va is the volume of HCl that completely reacted with sodium carbonate. And that one was given as 2Y. And we calculated that one from our experiment to be 10.10. Have you seen it? So volume of HCl now is 2Y. Then our volume of B is the volume of the pipette. Volume of pipette. And that one we use 25 centimeters cube. Pipette. That's what we used. And we had 2Y. Y represents our average titer in the phenolphthalein titration, which we got to be 5.05. So 2 times 5.05, that is equal to 10.10 centimeters cube, which we've already calculated over here. I hope you are following. So our concentration of B now becomes concentration of HCl Now, before we perform the titration, I said we are using 0.1 mole per decimeter cube HCl. So the concentration of HCl is 0.1 mole per decimeter cube. So our concentration of sodium carbonate becomes concentration of A, which we know to be 0.1 from our question, times volume of A, which we have as 10.10, divided by volume of B, which we know as volume of the pipette, 25, times 2. So we get 0.1 times 10. That will give us 1, divided by 1. Then we have 25 times 2, which will give us 50. So we are going to get 0.0202 mole per decimeter cube of sodium carbonate present. That is the concentration of sodium carbonate. Moving on to concentration of sodium bicarbonate. We are going to use the second equation. And as usual, we are going to call HCl A and sodium bicarbonate solution B. Amount of A divided by the amount of B. We have 1 mole of B reacting with 1 mole of A. So the mole ratio is 1/1. So we can say that amount of A is equal to amount of B when we cross multiply. So amount of A is equal to amount of B. But we know amount is concentration times volume. So amount of A will be concentration of A times volume of A. Amount of B will be concentration of B times volume of B. We can fix them into the formula and get CaVA is equal to CbVB. Now we are looking for the concentration of sodium bicarbonate, which is Cb. So our Cb becomes CaVA over Vb. As usual, our Ca is the concentration of HCl, which we are given as 0.1 mole per decimeter cube from our previous video. Then the volume of A, volume of HCl. Remember, we proved that the volume of acid that is required to completely neutralize our sodium bicarbonate is given as X minus Y, where X is our average titer from the methyl orange titration. And we had that one to be 21.05. Then our Y is the average titer from our phenolphthalein titration, which we had to be 5.05. So the difference will be 16 centimeters cubed. Then our volume of B will be the volume of the pipette we used. And that was 25 centimeters cubed. So we can fix these values into the formula. C of A is 0.1 times V of A, which is 16, divided by volume of the pipette, which is 25. Now this one will give us 1.6 divided by 25. 0.064 mole per decimeter cube. 0.064 mole per decimeter cube. So the concentration of sodium bicarbonate has also been calculated. If you want to know the masses, you can use the concentrations and the molar mass to calculate the mass density or mass concentration. Then with the mass concentration and the volume, we can calculate the mass. So this is how we use our double indicator titration, the continuous method, to calculate the concentrations of each of the samples that are present in the mixture. Don't forget, it's not like the normal titration, because here we have a mixture of two different substances. The volume of the acid that is required to completely neutralize all the sodium bicarbonate in the mixture is given as X minus Y, where X is the average titer from the methyl orange titration, and Y is the average titer from the phenolphthalein titration. But come to think of it, it really makes sense. It really makes sense, because in the titration, we started at 0.00. The first one, we had 5.30 as our endpoint for the phenolphthalein titration. Then we continued with methyl orange and got to 25.05. What did this tell us? It told us that the difference between the 5.3 and the 21.10 was as a result of the HCl reacting in the presence of the methyl orange. Yes, and it's the same thing that has been proven over here. X minus Y for all sodium bicarbonate, 2Y for all sodium carbonates. Go to the video once again, take your time, and you should get it right. Thank you.